We have three speakers today. We have Nuno, we have Jose, and we have Jose Andrade. Okay? So three people. Okay, so the next speaker is Nuno Araújo.
Right.
And you see, he's from Centro de Física Teórica y Computacional, Universidade de Lisboa, Portugal. That's very, very, very famous. And today he will speak about KiriNets, Kirielation, crystallation. Okay, so KiriNets, from folding nets to network of folding. Please.
Okay.
No.
Thank you. Is it working?
Yes.
I don't think is the microphone working? No. Yeah. Okay. So good morning to everyone. First of all, thank you very much for the invitation to be here today. It's for me a great pleasure to be back in Brazil. And today I would like to talk about something that we have been working on, that is to find strategies to obtain three-dimensional shape structures, like for example this cube or the soccer ball there, from the folding of a two-dimensional template, okay? And the two-dimensional template is basically a set of rigid panels connected through flexible hinges. I'm pretty sure that you have all played with a paper version of this Latin cross when you were a child, and the idea is to find ways to fold it into a three-dimensional shape, in this case the cube, and we are particularly interested in understanding this process at the micro scale, where you in principle you could think about obtaining the final shape from the thermal fluctuations, therefore from the random motion of the different faces. Okay, and this is something that we have been working together with several people, in particular also José Fernando Mendes, that is here in the room. So you can find examples of folding at different scales, and the idea is to be able to deploy materials with a certain shape, but using folding as the mechanism to obtain that shape. And here is just an example, the Webb telescope, that in order to deploy it in the targeted position, they decided to transport it in a folded configuration, and then it unfolded when it got to the final destination. And there are some challenges about what is the optimal way of doing this unfolding process. At the human scale, several examples come from robotics, and more recently people have been also developing ideas related to DNA origami, using DNA to build structures at the micro scale. I don't know why this is not working, but structures at the micro scale that resemble a paper folding, and you can use ideas from biotechnology to design these systems at the micro scale. But folding is something that strongly depends on the length scale. If you think about folding at the macroscopic scale, at the centimeter scale, typically occurs through stress relaxation, which means that the final folded configuration is unique and the folding path is also unique. If you now look into the nanometer scale, like for example in protein folding, then the final folded configuration is believed to be a minimum of the free energy, and it's known that the folding pathway will strongly depend on the interaction between the different components. At an intermediate scale, at the micrometer scale, then when we have these panels, the interaction between these panels is mainly an excluded volume interaction, and what drives the folding process is a sequence of irreversible bindings between the faces. Every time they touch, they bind together. And there are different ways to do it experimentally, but today I would like to focus more on the theoretical challenges. So the first theoretical challenge is saying, okay, I have a certain targeted structure. What is the template that can fold into that structure? And for the simplicity, I will be focusing on convex polyhedron. So like for example, the soccer ball. And in those cases, if you want to find what is the unfolded structure, or the template that can fold into this shape, one way to do that is to do a process named edge unfolding. So the idea is that you start with the targeted configuration, and then you keep, is this working? Okay, now it's working. So you start with the three-dimensional shape, and then you start to cut along the edges until you can open the structure. And we call to this open structure the net, and this is a set of rigid panels connected through the hinges. And so the way you do this cut cannot be arbitrary. There are a certain number of constraints that it needs to fulfill. The first one is that you want to have at the end a simply connected piece. The unfolding should be the union of the polyhedral faces, so you cannot cut along a face. And unfolding, once it opens, should not overlap. So you don't want that after it opens, that there is an overlap between the different faces. And so the first question is, does every convex polyhedron have a net? And we believe that the answer is yes, not because there is a formal proof, but because up to now, nobody has come up with a convex polyhedron for which we cannot find a net. But more interesting, even when you take the case of the cube, there are 11 non-isomorphic templates that can fold into the cube. And so in fact, what we are looking at is an n-to-1 problem, where we have n possible templates that can fold into a certain targeted structure. And if you think about obtaining the folded configuration from the random motion of the different faces, the question there will be, from all these 11 non-isomorphic templates, which one is the optimal one for folding? But if you take this very simple template and you connect the faces based on the letters that you see there, you get the vote. But if you get the very same template, but now you fold it in a different sequence, then what you get is the octahedron. And so what people have shown is that the final folded configuration depends not only on the template that we choose, but also on the experimental conditions. And if you think about thermal fluctuations, you expect that the folding process is a stochastic process. So one of the things that people have been trying to find, so what we are looking is the n-to-m problem, where n is the number of templates, m is the number of folded configurations, and the number m is even unknown. So we don't know what are the possible structures that you can get. So one of the first things that people did was back in 2011, a group from Johns Hopkins University was to try to identify criteria that will help us finding from all possible nets, which one is the one that maximizes the yield, the probability that you get the final configuration that you aim at. And they decided to compare two different compactness criteria. One is a topological compactness and the other one is geometrical compactness. Geometrical compactness is just saying the best template is the one that has the lowest radius of gyration. And topological compactness is saying, okay, we can define vertex connections as vertex that only need to close two faces in order to close all the edges around that node. And that's a vertex connection. And so the topological compactness is the net that maximizes the number of these vertex connections. The idea is that during the folding process, for this vertex to complete all the edges around, or to close all the edges around, you just need that two faces meet at a specific angle and they close, okay? Remember that this is irreversible, so every time, if two faces meet, they immediately close. And so the way they did it was experimentally. They considered different targeted structures. For each one of them, they considered 50 different templates for different, 50 different samples for different templates, 6 different templates, lowest radius of gyration, largest radius of gyration, the intermediate value, and the same for the topological compactness. And what they found is that the topological compactness is in fact a much more efficient criterion, much more effective criterion than looking into geometrical compactness. And this is where the ideas of networks come in, because the way they were identifying these optimal templates was just by random generating, doing this unfolding process at random, and then counting the number of vertex connections and picking the one that maximizes the number of vertex connections. But as you can imagine, as you increase the size of the structure, as you go to more complex shapes, then it takes much longer to build a catalog of all possible templates and therefore identify the optimal one. And the way they did it was basically generating some of them at random. And as you will see later, this is not a good strategy. So what we showed is that it's possible to solve the problem in a deterministic way if you map this problem into a graph. So the idea is that you represent the polyhedron structure as a graph, and you can, in fact, map it into two different graphs. One is the shell graph. So the shell graph, the nodes are the vertices, and the links are between vertex that share an edge. And then you also have the face graph, where the nodes are the faces, and then you have a link between adjacent faces. And so if you want to do the unfolding process, what you need to find is what are the edges that you need to remove in the shell graph in order to open the structure. And so we define the cut graph as being a subgraph of the shell graph that contains all the vertices and all the edges that need to be cut in order for the structure to open, and here is represented in red. So if you remove all these edges and nodes, then you can open the structure and get the Latin cross that I was showing to you before. Please. You can think about all possible of sets, the set of all possible edges that you need to remove for the structure to open, and doesn't need to be necessarily the minimum one, okay? But you are looking for those that lead to templates, okay? And that's what I'm going to say next, is that in order to guarantee that you get a template, again, you need to fulfill certain constraints. The first one is that it should span all vertices. If you assume that the curvature along every vertex is different from 0, it means that you need at least one cut in order to locally open the structure. So you need to span all the vertices. Should be loopless, because if you close the loop, you remove a face. And should be simply connected if you think about convex polyhedron. And so if you do that, what you are looking for is the spanning tree. So finding all possible templates is finding all the spanning trees of the shell graph. But remember, what they were looking for is the net that maximizes the number of single vertex connections. And a vertex connection is basically one vertex that only has one cut. And in the language of graphs, this is a leaf. So what you want is to find the maximum leaf spanning tree. Okay? And there are many algorithms that allow you to compute the maximum leaf spanning tree. Once you know that is a maximum leaf spanning tree, you can compute what is the ratio of templates, of what is the number of templates that are maximum leaf spanning trees divided by the number of spanning trees. And what you are seeing here is a plot of this number as a function of the number of edges. And you can clearly see that it decays exponentially with the number of edges, which means that if you try to do it at random, like they were doing before, you basically, the probability that you find the optimal configuration decays exponentially with the number of edges. And just to give you an example, if you take the dodecahedron, then you have about 2,000 maximum leaf spanning trees. You have 5 million spanning trees, which means that you need to generate, on average, 2,500 in order to find one that is the optimal one. In addition to that, you get a full catalog of all possible templates, so you can put on top of that another criterion, like, for example, optimize in terms of radius of gyration and so on. So you can do other studies on top of this. Okay, but so far I've been thinking about optimizing for folding efficiency, that you guarantee or you maximize the likelihood that you find the final targeted configuration. But you can also think for other applications in terms of folding time. And what we did is that in the beginning we just run some simulations in order to look to the folding time and look into these two different criterion. And in particular, what we did was to compare the top rank in terms of yield, in terms of percentage of configurations that led into the final folded configuration, and in terms of folding time, the ones that fold fast. And what we can see is that the rank is changed when you optimize in terms of the yield and in terms of the folding time. So what you can see here is that if you think in terms of folding time, the one that ranks in the 4th position in terms of yield is the one that is the fastest one to fold. So we decided to look into the problem and try to describe the kinetics of folding for these structures. And so the first thing we did was to look into a much simpler structure that is a pyramid. And for simplicity, what we did was to fix the base of the pyramid on a substrate, and now compute how does the total folding time depends on the number of faces. And what you get is that by running molecular dynamic simulations is that you get a non-monotonic dependence of the folding time in the number of faces. So initially it decreases and then it increases. And we did it in a way that the time is independent of the size of the faces. Okay, so it's written in units of time such that it does not depend on the size of the faces, and I will explain that later. So what we get is a non-monotonic dependence of the folding time on the number of faces. And in order to understand that, we focus on the pyramid with 3 different faces. And the relevant degrees of freedom here are the angles of the faces with the substrate. And remember that they are moving at random. And so if you look to the trajectories of the different faces, as I plot here, the angle as a function of time, we have 3 different faces, and they are doing a random motion. If I analyze the properties of this time series, what I see is that they are compatible with a confined random walk, because the faces can be between 0 and pi. And so what you see is that you have 2 different folding events. The first one is when the first 2 pairs of faces meet at a specific angle. And this is what I call the first closing event. So the first closing event is the first pair of faces, they close at a specific angle. And then you have the second closing event, that is when the third face comes and connects to the other 2, or binds to the other 2. And these 2 closing events are significantly different, and they can explain why we have this non-monotonic dependence. Let's focus on the first one. What do we want? That 2 faces meet at a specific angle in order for them to close. And so since the motion of the faces is uncorrelated, what we can do is to represent for each pair of faces the motion, the relative motion of the 2 faces in a 2-dimensional diagram, where in the horizontal axis I have the angle of one face, and in the vertical axis I have the angle of the other face. And so saying that they close means that if they move at random, this is a 2D random walk, and saying that they close means that the 2 will meet at a specific angle. So what we are computing is the time it takes for a random walk to hit this region for the first time. So it's a first passage process in 2 dimensions. And so now you have the possibility that every pair of faces is the first one to close. And so what you want is to do rank statistics and calculate what is the time it takes for the first pair to close. And so what you see is that you expect that the time it takes for the first pair to close scales with 1 over the logarithm of the number of pairs. If you now consider the following folding events, what happens is that now you already have 2 faces that are closed, and the other 2 just need all the other faces just need to touch this angle for the first time. So what you have in that case is a random walk in 1 dimension, and you are calculating how long it takes to reach the specific angle, and therefore is a first passage process in 1D. And the time it takes for the last one to occur, because you are looking to the full folding, so you need to wait for the last phase to close, then it means that the total folding time should scale as the logarithm of the number of remaining phases that you have to close. Okay? So you expect that the total folding time is the sum of these 2 times. The time it takes for the first pair to close, plus the time it takes for the last phase to close. And so let's go back to the folding time as a function of the number of faces. And so basically what you get is that the purple line is the time of the first folding event, and the green line is the time of the final folding event. And the sum of the 2 is the solid line that corresponds to the total folding time. And the data points that you see there are simulations for different sizes of the faces, different closing angles, and so on. So you can clearly see that this non-monotonic behavior results from the fact that the rate limiting process for low number of faces is that you have 2 faces that first meet. But if you increase the number of faces, then the likelihood that the last one will take a long time to close is increasing with the number of faces. And that's why it goes up again. Okay, but this is just for the pyramid. If you want to go to more complex shapes, even if you want to go to the case of the cube, you need to identify all the folding paths that allow you to go from the template to the final folded configuration. The advantage here is that the folding is driven by this irreversible binding between the faces. And so if it is driven by this irreversible binding between the faces, means that you can go from a continuum configurational space to a discrete configurational space. Because having this structure or any other equivalent structure for which I keep the same number of connections is the same. So what we are showing here is all the possible intermediate configurations that allow you to go from the template to the final folder configuration in the case of the cube for one of the 11 possible templates. And the problem is how to obtain this folding landscape. And again, if you do it completely at random, trying to check all possible ways to cut from the cube to the template, then this is an impossible task, because even for the case of the cube, for a single template, there are 7 edges that you need to cut, so it's 7 factorial, so you have something of the order of 5,000. So what we did was to come up with an efficient algorithm based on graph theory to identify all these cuts, and I'm just going to show you what are the main features of the algorithm. The first thing that you need to check is what are the possible cuts that allow you to open a structure. If I take a cube and I just cut one edge, this is not enough to open the structure, okay? So you need at least 3 cuts in order to open the cube. As you can see, well, in this case it's more, but you need at least 3 cuts in order to open the cube, okay? And so you can now define how many edges you need to cut and how many ways you can cut the cube in order to open at least one face, and you can do that for all possible states. Here is just a summary of what you can do, and you can look into possible combinations of these cuts and see what type of intermediate structures you get. Well, one thing that you need to do is to find a way to identify uniquely a certain configuration, because you can cut in different ways and get exactly the same configuration. And so the way to do that is to represent the cuts as a binary number, where for each edge we have a 0 if it's not cut or 1 if it is cut, and then we find that, and then we get that for every sequence of cuts there is only a unique number characterizing that cut, and we just need to check if that configuration was already found or not. Then you see that the intermediate folding states correspond to the configurations that I find by performing these cuts, but I need to be aware that they might be isomorphic, which means that, for example, if you take the case of the cube, I can remove 4 different faces if I start from the Latin cross, but they are the same configuration. And the way to do that is that I have isomorphic graphs, meaning that the 2 graphs are equivalent just by swapping the labels of the nodes. And so you need also to find these isomorphic configurations. Here is just a summary of what you get. For every folding configuration, you can look of all possible states that can be cut. In the case there are isomorphic configurations, you can also group them. And at the end, you find the full configurational space for the cube. In this case, when you consider no misfolds. So you only look to trajectories that take you to the cube. Then you, please go ahead. Graph, the topology is the same. You can get there from different ways, exactly. But at some point you get something that is similar, just because in one case this is the face that is open, and in the other case it's just the face on the other side. But the 2 are the same, because when you look to the graphs, you change the labels and you get... Exactly. So we get thousands of configurations and we start to group them based on symmetries that we have there. So in this case it's for the cube, where I have neglected misfold configurations, but I can also add the misfolded configurations here in orange. Like, for example, if I start with this case, this guy here, sorry, this one. This guy here is a misfolded configuration. Once I get this, I cannot go back to the cube without breaking a bond, and therefore is a misfolded configuration. That one is represented there, and we can map all possible configurations, and we can do it in a very fast way. We can do for all types of shapes. You can take the picture of an object, you can triangulate the surface of the object, and you can ask what is the template that folds into that and find all the possible folding paths that you need to do. Maybe one day you go to IKEA, and instead of being connecting pieces, you will be just folding your table or your chair. Okay, here is just an example for a template that can lead you into the octahedron or the boat, and also the possible misfolds. And now, what you have here is a directed graph that is weighted, where the weight of the links is the probability that when you are in this configuration, that you get one of the other configurations. And you can now think about using graph ideas to optimize the kinetic paths and think where do you need to intervene in order to make it that it does not get trapped into a certain configuration, or that you avoid misfoldings. Thank you very much. So just to wrap up, folding is an end-to-end problem. I hope that I have convinced you that you can use ideas and methods from graph theory to look into this problem. We are just in the beginning. There are many, many things to do there. But what we have found so far is that finding the optimal nets correspond to find the maximum leaf spanning trees. But when we look to optimization in terms of folding time, then it's very different to look in terms of yield, and we need new methods. And the first thing that we did was to find this folding landscape, and that the folding landscape can be mapped into a discrete weighted graph. So thank you very much for your time, and I will be happy to answer your questions.
Thank you a lot. Fantastic.